You will be investigating sodium, which is an alkali metal, and calcium, which is an alkaline earth metal. Sodium is the more reactive metal, so it has to be stored under oil. And when you remove a piece, you use some tweezers and then place that piece on a paper towel and tap off the oil. This small piece of solid sodium is dull and gray because its surface has reacted with the environment, but we can easily cut through this piece with a scalpel knife and briefly expose the appearance of pure sodium, which is lustrous and silver-colored until it will react with the environment. And the chemicals in the environment that the pure sodium surface reacts with are oxygen and humidity, which is water vapor. You may have seen in high school that sodium reacts vividly with water. So we fill some Erlenmeyer flask with water and add some drops of an indicator called phenolphthalein. This indicator is reacting to a low acidity and turns pink in alkalinic, also called basic solutions, when there's very low acidity in the solution. So watch what happens when we add a small piece of sodium to the water in the Erlenmeyer flask. Well, you can make out that little piece there as it dances on the surface of the water because sodium is less dense than water, so it will not sink in water. And you can see how it becomes increasingly more pink, so it reacts with the water and produces something that makes the water alkalinic or basic. The alkali metal sodium has reacted with water and formed sodium hydroxide, which makes water alkalinic. We can determine the pH, which is a measure of the acidity, using universal pH paper. Dipping a strip into our solution and comparing the resulting coloration to the matching color scale on the package allows to identify a pH of about 12, which is significantly greater than a neutral pH of 7, and therefore another indication that our solution is alkalinic. Now we generate observations for a metal from the neighboring main group in the periodic table for one of the alkaline earth metals, calcium. Calcium is not stored under oil, which means it does not react as easily as sodium. Cutting through a piece of calcium will not work with a scalpel knife, but if you scratch off some of the oxidized surface, you can see that it is also silver-colored and lustrous, but obviously much harder than sodium. Watch what happens when a small piece of calcium is dropped into a test tube half filled with water. The calcium surface has a hard coating of corrosion products, and it takes a few seconds for these to dissolve. So initially only small spots of calcium react, forming only a few small hydrogen bubbles. When all the pure calcium is exposed, the reaction occurs more vividly and larger hydrogen bubbles are forming. Now an empty test tube is placed on top of the opening of our reactor test tube, and the emerging hydrogen gas can displace some of the air in the empty test tube. After the gas formation has stopped and all calcium has reacted, the test tube containing the hydrogen gas is kept upright and placed on the table. To prove that it contains hydrogen gas, we perform the hydrogen pop test. We ignite a long match and then simultaneously insert the burning match as we turn the test tube into a horizontal position. It is important to insert the burning match before the test tube is horizontal so that the hydrogen gas does not escape. The sodium produced sodium hydroxide and the calcium produced calcium hydroxide, and as you can see, not all of it is soluble. The dissolved hydroxide ions from the calcium hydroxide should make the solution alkalinic as well, and we can test that by adding phenolphthalein. Hydroxide ions react with hydrogen ions to form water. By adding hydrochloric acid, which is of course a perfect source for hydrogen ions, we remove the hydroxide ions, and that causes the precipitate to dissolve and form soluble calcium chloride. All solutions from this experiment can be flushed down the sink, and the test tubes get discarded into the glass container.